All right, so at the end of the previous video, we were looking at the ideal gas law, so PV is equal to nRT. And later on in this chapter, kind of near the end of it, we'll look at this equation and apply it to real gases. So there's going to be kind of correction factors, because with this ideal gas law, we're assuming ideal behavior. And in reality, that's not going to be the case. It does a pretty good job of describing the properties of a gas sample, but it's not perfect. And that's because we're making a few assumptions here. So primarily the collisions are elastic. So when we're thinking about these gas particles, they're going to be moving around, and that means they're going to bump into each other. They're also going to bump into the walls of whatever container they're in. So if they're in a balloon, they're going to be hitting the sides of that balloon. And in the case of collisions being elastic, that means there's going to be no loss of energy. When in reality, there's going to be like a small amount of heat loss, friction, whatever it may be. So the collisions just aren't going to be perfectly elastic. Volume of the gas particles is negligible. So this is just meaning that the particles themselves, so the nitrogen molecules or oxygen, whatever it is, are going to be so tiny that they essentially take up no space. Again, there's going to be a correction factor for that in the equation above. And then no intermolecular forces. So if you think about putting water in a pot on the stove, start heating it up, eventually it starts to boil, because what we're doing and what we'll talk about in the next chapter is intermolecular forces. So it's actually holding together those different molecules. So initially in the liquid water, they have some amount of kinetic energy, but as we heat them up, we give them more and more energy. We spread those molecules further apart. We break those intermolecular forces. So the reason we say gases fill the entire shape, entire volume of whatever container they're in is because once we get that substance above its boiling point, we've essentially completely broken that intermolecular force. And now those molecules are independent of each other. There's nothing holding them together anymore. And in reality, that's not going to be entirely true. So there's going to be, again, another small correction factor. So with this ideal gas equation, like I said, it does a pretty good job of estimating or describing the properties of a gas sample. But it's going to be better when the gases are under more ideal conditions. So if we think about a um, all right. So if we think about a phase diagram, so we'll have temperature here, pressure here. So we've got this phase diagram here. So if we think about where these different phases would be, so we've got temperature increasing on the y-axis, pressure increasing on the x. So at this far right corner, we've got relatively low temperatures and relatively high pressure. So what we're going to see there, that's a terrible S. But this is going to be kind of the section of whatever the substance is where we're going to see it's going to behave as a solid. So low temperature, high pressure. We don't have those molecules with much energy, and we're packing them in tightly together. So then as we move to this middle section, now we've decreased the pressure slightly, we've increased the temperature. Now we're going to see these are our liquids. So our final section here is going to be our gases. And if we think about it, that makes sense. So we've got relatively high temperatures and low pressures. So we're going to have these molecules moving quickly, or atoms. But there's not really going to be that pressure squeezing them together. So that's why we're going to have them moving apart. That's going to be our gases. So when we're looking at this ideal gas equation, it's going to work best under ideal conditions, which is going to be this section of the graph. So we want higher temperatures and lower pressures. That's going to allow the gases to behave more ideally, because it's going to allow them to spread out further. It's going to make the size of the particles relative to the size of the container less or more negligible. And then by doing that, allowing them to spread out from each other, it's going to decrease that intermolecular force even further. So we're going to see that this equation becomes better at describing that gas. And then also with this equation, we're going to see how we can kind of manipulate it to figure out what type of gas we have in a particular situation. But in the form we see here, pressure, volume, moles of gas, the gas constant, and temperature, no piece of it is specific for helium or ammonia or oxygen gas. Because we're assuming that all of these gases are going to behave identical. Again, with the correction factors, they are. specific to the gas. There's a slightly different correction factor for these three in reality. But in the ideal case, they're all going to behave identical because there's no intermolecular force between any of these different molecules or atoms in the case of helium. And then with it, we also have what's known as the molar volume of gases. So sometimes we say gases occupy 1 mole of any gas occupies 22.4 liters. But just note when we're saying that, we're referring to STP, which is standard temperature and pressure. So we'll see that a couple of cases later on. But when we're at STP, we're thinking about 0 degrees Celsius. So when we're plugging into a gas equation, 273 Kelvin, and then 1 atmosphere of pressure. So that's sea level pressure. Because if we change the temperature or pressure, we're going to have the gas expand or compress depending on what we do. So when we say 22.4 liters for 1 mole of gas, that's just for STP, so standard temperature pressure. But like I said, we're going to be able to manipulate that equation and actually get information about a particular gas, so we can figure out the density of a particular gas by inputting the molar mass, and we'll also see later on we can identify a gas by solving for the molar mass there. So just looking at the equations here, again, regular ideal gas law at the top, and then we've got the density equation here. So what we're doing in this case is essentially solving for volume here, so dividing both sides by pressure, and then inputting that whole thing, so nRT over volume, or nRT over pressure, excuse me, because we're solving for volume. And then we're just substituting that in for volume. So that's why we've got mass times pressure over moles, gas constant, and temperature there. And then with this piece of it, so mass over moles, just separating it out there, that's just going to be representing our molar mass. So grams over moles, molar mass there. So when we're solving for density of a given gas, if we know the molar mass of that gas, because if you think about it, that's going to give us the information about moles and grams. If we know the pressure, gas constant we'll always have, assuming that we've got pressure in atmospheres. And then temperature, we're going to have in Kelvin. So with this, again, going back here, so density is equal to the molar mass times pressure over the gas constant times temperature. So if we're looking at a question like this, what is the density of molecular nitrogen at STP? We need to remember a couple things. First, what STP is. So again, 0 degrees Celsius or 273 Kelvin or 273.15 Kelvin. And then 1 atmosphere. And then we also need to remember that nitrogen is going to be diatomic. So when we're calculating the molar mass of nitrogen, we need to account that there's going to be 2 of those nitrogens rather than just a single one. So when we go to plug this in, 28.01, because again, each of those is going to be 14. Depending on what periodic table you have, you may have more or less of the digits. And then again, STP, so 1 atmosphere, 273 Kelvin. And with this one, just pay attention to the units, because with the molar mass, we had 28.01 grams per mole. And then with the gas constant, we've got the volume unit of that in liters. So when we go through and actually plug everything in, moles is going to cancel. Atmospheres is going to cancel. Kelvin is going to cancel. So the only thing we have left on top is grams. The only thing we have left on bottom is liters. So when we solve for it in this case, our units are going to be grams per liter. So it's going to be important that we pay attention to those units. Because if we solve for the molar mass in kilograms instead, so if we had 0.028 kilograms, then our units here would have been kilograms per liter. And then again, also just paying attention to the units when we think about something like water, liquid water. We say it's got a density of 1 gram per milliliter. About, depending on the temperature, it fluctuates a little bit, but it's about 1 gram per milliliter. But that's 1 gram per milliliter, where this is 1 gram per liter, so 1,000 times the volume, with about the same amount of mass. So these gases are going to be much, much lighter than we see with those liquids. So as you're going through and solving for these, pay attention to the units and just think about, does that value make sense at all? About 1,000 times lighter than water makes sense for this gas. But if we got 1.25 kilograms per liter, then we would know that's just much too high for a gas sample. So if you want to practice with the next one, kind of the same idea here. We've just got to remember temperature, we're going to convert to Kelvin. Pressure, we're going to convert to atmospheres. I guess with the pressure one, if we had the gas constant that included torr, we wouldn't need to do that. But we're typically just going to use this value, or 0.08206. Depending on where you round, you'll see different numbers there. But just like with the nitrogen, we want to remember that hydrogen also going to be diatomic. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, Brinkelhoff, I think I got all of them, are going to be our diatomic elements. So when we're calculating the molar mass, again, we don't want just one hydrogen. We need to account for two of them. But that means we'll have a molar mass of 2.016 grams per mole. We'll still have 1 atmosphere for the pressure because 760 torr is actually just equal to 1 atmosphere. We'll still have 0.08206 or 0.0821, however you want to round it there. And then for the temperature here, since we've got 17 degrees Celsius rather than STP, we would have 290 Kelvin. And then when we plug all that in, we'll get a value of 0.0847 grams per liter. And it makes sense that this is going to be smaller now because the mass of hydrogen is going to be 2 compared to 28, so it's 14 times smaller on top. And then we've got a temperature that's slightly higher. So with the hydrogen calculation, we've got a smaller number in our numerator, a larger number in our denominator. So it makes sense that we get a smaller pressure there, or a smaller density. And then kind of a similar manipulation of the ideal gas law allows us to actually determine what a gas is, or at least determine what sample a gas isn't, or identify what it possibly could be. So this won't definitively allow us to determine what a sample is just by itself, but it can be a useful piece of information. Because what we can do is, again, arrange this equation, thinking about the molar mass is equal to mass over moles. And then with it, it might be easier to actually kind of think about the substitution in this case. So moles, we've got N in the equation. Moles is just equal to mass over molar mass. So if we again substitute that in for moles here, now in this case, the equation at the bottom, we're just rearranging this to solve for that molar mass. So if we've got all this other information, we can determine what the molar mass of a gas sample is. And then in that case, we can at least eliminate different options if they just have a different molar mass. There are gases that can have the same molar mass, so this in itself can't 100% say what a gas sample is, but we can use this to help us identify what it possibly could be. So if we look at this one, cyclopropane, a gas once used with oxygen as a general anesthetic, is composed of 85.7% carbon and 14.3% hydrogen by mass. And cyclopropane will be a hydrocarbon, so it's only going to be those two, and that's why carbon and hydrogen just add up to 100%. But we want to find the empirical formula so we want to find the empirical formula just using that information. And then if 1.56 grams of cyclopropane occupies a volume of 1.00 liters at 0.984 atmospheres and 50 degrees Celsius, what is the molecular formula for cyclopropane? All right, so for this one, we've got to do a little bit of work, and I'm going to type it out just so it's hopefully a little bit neater than when I try to write with the mouse. But with this one, we got to do a couple different things. Thinking back to one of the chapters from Gen Chem 1, we've got to use the mass percentages to figure out what the empirical formula is. So what's the simplest ratio of carbon to hydrogen? And then we'll be able to use that information. We'll be able to use the ideal gas equation to figure out the molar mass, and then molar mass empirical formula, we can get the molecular formula. So for this one first, remember, we can turn those percentages just into grams. So we'll have 85.7 grams of carbon rather than 85.7%. So we're just assuming if we had a 100-gram sample, 85.7 grams of that would be carbon. And if we're dividing by the molar mass, 12.01, that means we're going to get a value of 7.13, and I'll be 7.14 actually. And we can do the same thing with the hydrogen, 14.3 grams, and we'll divide by the molar mass again, 1.008, and that will give us a value of 14.2. So with this one, we'll divide by the smallest value, so 7.14, going to equal 1. Again, divide by the smallest value to give us whole number ratios, hopefully. And of course, 14.2 divided by 7.1, going to give us 2. Of course, this won't be even 2, but it's going to be 1.99 essentially. So we're just going to round it to. So in this case, this means our empirical formula is going to be CH2. For every carbon, we're going to have 2 of these hydrogens. All right. And then we can look at the second half of this question. If 1.56 grams of cyclopropane occupies a volume of 1 liter at those conditions, we can think about what our molar mass is going to be, or we can solve for our molar mass at least. And in that case, we'll have M molar mass is equal to MRT divided by dV. Oops. Insert. All right, so now we've got molar mass is equal to the mass, 1.56 grams times 0.08206. And I'm not going to put the units there just because that's going to be a hassle to type. And then we've got a temperature of 50 degrees Celsius. Remember, we want Kelvin. So 50 plus 273 gives us 323 Kelvin. And then on the bottom, we've got a volume of 1 liter, 1 times anything, and a pressure of 984 atmospheres. Oh, I got 6,240. I knew that was wrong, but it's because I did division at the very beginning. All right, now that I've fixed that, we should get a value now of 42 grams per mole. So like I said, initially I got 6,000 just because I had division there, when it should be multiplying on the top, of course. But now we've got an empirical formula of CH2, so 1 carbon for every 2 hydrogens. We've got a molar mass of the actual molecule. Every mole of it weighs 42 grams. So what we've got to do is figure out for the empirical formula, what is that mass? So 1 carbon plus 2 hydrogens is going to be about 14. So I'm rounding this just to make it easy. So if we've got a molar mass for the empirical formula of 14 grams, but the actual molecule weighs 42, 42 divided by 14 is just 3. So that means this actual molecule is 3 times larger than the empirical formula. So we would just multiply that by 3. We're going to get a formula of C3H6. Again, we still have that same ratio, 1 carbon for every 2 hydrogens. It's just 3 times as large. And then if you take organic chemistry, cyclopropane, the cyclo piece you'll learn just means it's essentially a ring structure. So all those carbons are just connected in a ring, basically. And then propane, that prop prefix just refers to the 3 carbons. So we've got 3 carbons in a ring, and then each of those carbons is just going to have 2 hydrogens attached to it, in addition to be attached to the other carbons, of course. All right. Then we look at the actual, we look at the actual work, and we can see essentially the exact same thing. So again, we rounded it just to 2 immediately, but that calculation just came out to 1.98, so that's why we just rounded up to 2. But then going through everything else exactly the same, get to that formula C3H6. All right, so if you want to practice with one on your own, feel free to pause the video. Otherwise, I'm just going to go ahead and do the same thing. This is going to be a very similar question. It's just we've got a different percentage of carbon to hydrogen. So 92.3 grams divided by 12.01 for the carbon. And that will give us a value of 7.69. And then for the hydrogen, 7.7 grams divided by 1.008. Oops, is going to give us 7.6. So in this case, it's just going to wind up being empirical formula of CH. So you can see those numbers are essentially exactly the same. So of course, if we divide 7.64 divided by itself, we'll get 1. And then 7.69 divided by 7.64, we'll get just barely over 1. So we'll just round it to 1. So in the actual molecule, we'll have 1 carbon for every hydrogen. Whoops. But again, we would use the ideal gas law to actually figure out what the molar mass is going to be. So we can think about how much do we have to scale up that empirical formula. And again, the molar mass is going to be equal to 1.10 grams times 0.08206. And we've got a temperature of 59.5. So that'll be 332.5 Kelvin. Or I guess 7 Kelvin, 0.15. Double check that that's correct. 273.15 plus 59.5. Yes. All right. And then we'll divide by the pressure and volume. In this case, just going to be 1.15. So I'll keep the units out on the bottom there just because we're going to multiply these two together to get 1.15 liter atmospheres, really. But now when we do that, we'll get a molar mass of, I'm going to guess 26, because I think I remember the formula for this one. 26 times 7. Yes. Whoops, not 62. We'll get a molar mass of 26 grams per mole. So again, if we go up here and think about the molar mass of the empirical formula, we're going to have 1 carbon plus 1 hydrogen. It's going to be 13 grams per mole. So this molar mass, the actual molecule, is twice as large as the empirical formula. So instead of 1 carbon and 1 hydrogen, we'd have 2 of each of those. And again, really would be subscripts. I'm just not going to do it because we'll see the exact same thing on this slide here. So even though the ideal gas law isn't specific to any type of gas, we can kind of rearrange that mole piece of it in order to use that molar mass to help us get information about that particular substance. All right, so looking at the next piece, determining the molar mass of a volatile liquid. So we can see the procedure here. And volatile, if you're not familiar with that term, essentially just means that that liquid can evaporate fairly easily. It can get into the gas phase. So thinking about pesticides, what I've worked with in grad school, there's volatile pesticides that easily get into the gas phase, semi-volatile pesticides, which still pretty easily get into the gas phase, and then what are known as non-volatile, which essentially just will not get into the atmosphere, other than if they're just physically swept up, but they won't move from like solid or liquid into the gas phase typically. So with this one, we're looking at volatile liquids, so things that can evaporate. So if you do take organic chemistry, a lot of those substances are going to be highly volatile, meaning that they're going to get into the gas phase easily. That's why a lot of solvents or organic solvents, you can smell them quite easily just because they do get into the gas phase. so readily. All right, so with this process, essentially what you're going to do is just put a sample of whatever that substance is in a flask. So this is just a round bottom flask. And then they're just poking a small hole with a syringe in the top just to allow that gas to escape as we heat it up. So in this picture here, you can just see it's on a hot water bath on a hot plate. So we're just using the water to heat up this sample. And basically what you're going to do is as that last little bit of the liquid turns into the gas phase, you just cap the sample, cap the flask, I should say. Because with it, what we're kind of assuming is the gas in the flask, since we're allowing it to escape, is going to be the same pressure as the atmosphere. So if we measure the temperature of the gas at that point, think about the volume of the flask, we can already know that. But the temperature, we'll know just based on its boiling point. The pressure, that's what I was trying to think. The pressure, again, we're just assuming since it's allowing it to escape is going to be the same as the atmospheric pressure. And then we can get the mass of the gas by just, since we cap it, just eventually going to cool, it'll return to the liquid. We can just, and I guess you could even do it in the gas phase because it'll still be in the flask. But the glassware itself may still be warm, so you'd want to let it cool down not to damage the balance. But since we cap it, that gas is gonna recondense. So it's gonna stay in the flask. We're gonna be able to measure that mass. So if we look at a question like this, using this procedure, a sample of chloroform gas weighing 0.494 grams is collected in a flask with a volume of 129 cubic centimeters at 99.6 degrees Celsius when the atmospheric pressure is 742.1 millimeters of mercury. What is the molar mass? So again, we're going to use that molar mass kind of version of the ideal gas law. So molar mass is equal to mass times the gas constant times temperature divided by pressure and volume. But what we got to do is change some of these units. Because the millimeters of mercury, we need to get that into atmosphere. So we're going to divide it by 760. Remember, there's 760 millimeters of mercury or 760 torr in an atmosphere. So if we divide that by 760, we'll get 0.9764 atmospheres. And then the temperature, Celsius, we've got to convert it to Kelvin. So to that 99.6 degrees Celsius, we'll add 273.15. And we're going to get 372.8. The cubic centimeters, remember a cubic centimeter is really a milliliter. So if we've got 129 cubic centimeters, we have 129 milliliters, which means we've got 0.129 liters, because our gas constant is going to be liter atmosphere per mole Kelvin. But now that we've changed those units, we've got mass. So we'll do mass times the gas constant times temperature divided by the pressure and volume to get the molar mass. So let me just erase this because we'll have the equation on the next one. All right. So again, we'll just rearrange it to get the equation we saw on some of the previous slides. Mass times the gas constant times that temperature, again in Kelvin, pressure in atmospheres, volume in liters. So we get a molar mass of 120 grams per mole for chloroform. And with chloroform, I believe it's 3 chlorines, a carbon, and a hydrogen. So that value makes sense because the 3 chlorines would be 105-ish, or 106. Carbon would be 12. Hydrogen would be 1. So it makes sense that we get about 120 there. So then with the next one, kind of the same idea, sample of phosphorus that weighs 3.243 times 10 to the negative second grams. It's really 0.03243. So it's really not, it's really more work to kind of write that value in scientific notation. but it exerts a pressure of 31.89 kilopascals in 56 milliliters at 550 degrees Celsius. And again, we want to get the molar mass. We want to figure out the molecular formula of the phosphorus vapor. So for this one, we can do essentially the exact same thing. So let me do this. 0.03243 grams times 0.08206 times. So the temperature, we need to get that into Kelvin. So 550 degrees Celsius is really 823 Kelvin. We're going to add 273 to that value. And then with the volume, we've got 56 milliliters. So that'll be 0.0560 liters. So with the kilopascals, if you don't remember the conversion for this one, we'll have it on a quiz or a test. But it's going to be 101.325 kilopascals for every atmosphere. So we'll divide 31.89 divided by 101.325, and we'll get 0.3147 atmospheres. So when we go through and plug all this in, we'll get 0.03243 times 0.08206 times 823, so a very high temperature, divided by 0.0560 divided by 314. Okay. So we'll get a formula of 124.3. And with it, I'm just going to add this to 124 since we only have 3 sig figs in the temperature here. So we'll get 124 grams per mole. So that's the molar mass. And now if we want to get the molecular formula, it's a phosphorus vapor. So we're just assuming it's only phosphorus atoms. So we need to figure out how many of the phosphorus are in this molecule. Because if we think about oxygen or nitrogen, it's diatomic. We've got 2 of them. So in this case, we can do 124 divided by the mass of a single phosphorus, 31. And that'll give us 4, which means the formula for this would be P4. With just the subscript. All right. And with the gases, we've got another law. We've got another equation, and this one's going to be what's known as Dalton's law of partial pressures. We've already seen this one in the lab. So when we solve for the gas constant, the reason we were able to do that is because we said the pressure in the flask was equal to the pressure in the room, so just the atmospheric pressure. But then in the gas, or in the flask, excuse me, we had water vapor and then oxygen. So because we knew the temperature of the water, we could figure out the vapor pressure of oxygen. And then we were able to figure out the pressure of, or the vapor pressure of water, excuse me. So then we were able to get the pressure of oxygen there. So when we're looking at Dalton's law of partial pressure, it's essentially just saying if we have a mixture of gases, the total sum, or the total pressure of all of those gases is just going to be the sum of each of those individually. So in this case, if we had a canister filled with gas A, B, and C, and gas A had a pressure of 300 kilopascals, B was 600, and C was 450, we could figure out the total pressure of that mixture just by adding each of those together. So 600 and 450 gives us 1050. 1050 plus 300 gives us 1350. So that's what we can see here. So it's just looking at each of those individually to get the pressure of the total gas. And with it, we can also use mole fraction to help us figure this out. So looking at the equation at the top there, that's just our mole fraction. So X is just, or X1 in this case would be the mole fraction for gas 1. So it's the moles of gas 1 over the total moles of gas. And what we can do is take that mole fraction and sort of relate it to the law of partial pressure. Because if you think about the gas law equation, PV equals nRT, it's just based on moles. It's not based on moles of this particular gas. So we can take this mole fraction, kind of connect it with Dalton's law of partial pressure, by just saying the mole fraction times the total pressure gives us the partial pressure of that particular gas. And the reason we're referring to it as partial pressure in this case is because if we think about this mixture, of this 1350 kilopascals, only 450 of it's going to be coming from this gas, or 600 from this gas. So it's only providing a partial portion of the total sum. So that's why we're just referring to it as partial pressures there. It's just one portion of the total mixture. But again, if we know the total pressure and we know the mole fraction, we can figure out the individual pressure of that gas. Or again, just three variables. If we have any two of them, we can solve for that third one. So if we know the pressure of a given gas, we know the pressure of the entire mixture, we can figure out what portion in terms of moles is that gas. So if we look at the question here, a 10-liter vessel contains 2.50 times 10 to the negative third moles of hydrogen, 1 times 10 to the negative third moles of helium, 3 times 10 to the negative fourth moles of neon at 35 degrees C. What are the partial pressures of each of these gases? What is the total pressure in each, or in atmospheres? So with this one, there's actually kind of two ways we could go about it. If we solve for it in terms of A and then B, we have the number of moles of each of these gases. We have the temperature they're at. We have the volume. So what we could do is for each of these individually, solve for the pressure. And then we could just add the pressures together to get part B. Or what we could do is do the ideal gas law one time. So add all of these moles together, plug that into the ideal gas law, get the answer for B, and then using the mole fraction, get the answers for A. So depending on kind of which order you wanted to solve for these in, would just kind of affect the way that you'd want to approach it. So with it, I'll show the second way, because the next slide will have the first one. But if we think about the total moles, we've got 0.00250 moles of H2 plus 0.000 moles of He plus 0.0003 moles of neon. So altogether, we're going to have 0.00380 moles. Yeah. So now when we think about PV is equal to nRT, we're looking for the total pressure. So we can do nRT divided by volume. So now we know the total number of moles, 0.0830 moles. The gas constant, I'm just going to put R since it's always going to be. Oops. And then the temperature, 35 degrees Celsius. So again, we got to make sure we convert that to Kelvin. So we'll have 308 Kelvin divided by 10.0 liters. And with it, let's see what that gives us. Oh, 6 times 308. Oh, so sig figs. So we'll do 3 sig figs, so that's 4.026. And then this is going to be in atmospheres. Let me drag this way. All right. So now we've solved for the total pressure. But if we want to get the individual pressure, we need to get the mole fraction. So for H2, we would have 0.0025 divided by 0.0038 times the total pressure. So it should be a relatively large portion of that total pressure. Since this is about 2/3 of the moles, but 0.00426, so it should get 0.00280. And then it would be the same idea for helium and neon. It's just with those ones, we've got a different number of moles. So for this piece of it, we would have a different number there. But the total number of moles is the same, so 0.00308 is the same. The total pressure would be 0.00426. But now if we look at this slide, this one just went about it in the opposite way. So this one actually solved for it in terms of A and then B. What I did was solve for it in terms of B and then A. 426, what did I? That looks like, where did I screw this up? Because the total pressure they're getting here is twice the volume, so or twice the pressure. So I'm trying to see what could have affected that, or did I just plug something? Oops. All right. So with this, I just plugged something in right. It's set up right, but I just apparently can't type in a calculator. So the initial pressure there, I just got about 40% what it should have been for whatever reason. So when we actually plug this one in, everything in terms of the setups is the same. So solving for the pressure was correct, just the value is wrong. So that's why we're changing it in the mole fraction part of it. So what we would see in that case is 0.025 divided by 0.0038 times 0.0096. It's still about 2/3, so we get 0.062 in that case. Yep, all right. So something just went weird with the first calculation. But again, this one, just going B and then A. So solving for the total pressure by just adding all of the moles together and just keep treating that as one giant mixture. And then using the mole fraction of hydrogen to figure out just the portion of hydrogen. And then we get the partial pressure for helium and neon, just using those mole values instead of 0.0025. But in this case, just doing it in the opposite order, I think it's a little bit more work just because now you have to do the gas law equation 3 times. But then it does make that second step easier because you can just add up those pressures rather than using the mole fraction. But either way, we're ultimately arriving at the same place. We're just going in two different paths. But again, this one, just looking at each of these samples individually. So that's why we're using the moles of each of just the helium or the hydrogen, neon, whatever it is, getting the pressure, the partial pressure for those gases. And then with the total one, just using Dalton's law of partial pressure, adding them all up to get the overall mixture. All right. So if you want to practice this one as well, you can do the same thing. I'll just go through this one quickly. And again, I'm just going to do it the way I did the previous one. So I'll do 0.0388 plus 0.147 plus 0.0803 gives us 0.2661. That's going to be too many moles, or too many sig figs rather. So I'll do 0.226 moles total. So when we use the gas law, what are we looking for here? Pressure. So I'll do pressure is equal to 0.266 moles times R times the temperature, which in this case would be 25 degrees Celsius or 298 Kelvin. And then we'll divide that by the volume, 5.73 liters. So we get a total pressure. 206 times 298. We get a total pressure of 1.13. Actually, we'll round that up to 1.14 atmospheres. And now for the pressure of each of those gases individually, pressure of N2, we'll just do 0.0388 divided by 0.266 times the overall pressure. And again, it would be the same thing for the other gases. It's just instead of 0.0388, we'd use the number of moles for those. But with it, we'll get 0.166 atmospheres. For the nitrogen, I guess in this case, we just needed that total pressure. Yeah, so this one actually started going too far because we just need the total pressure. So we're just looking at this value here. And then with their answer, I actually disagree with this slightly. They've got too many sig figs. Because when we're adding up the moles here, 0.388, 0.0388, 0.147, 0.0803, this only has 3 digits after the decimal. So when we add those, we can't keep the 8 at the end or the 3 at the end here. So we would have 3 sig figs in our moles. We should have 3 sig figs in the atmospheres as well. So the textbook, I would say, is incorrect in terms of the sig figs. All right, and we'll go a little bit. All right, so looking at this one now, this will be the last example we look at. A gas mixture used for anesthesia contains 2.83 moles oxygen and 8.41 moles of nitrous oxide, which has a formula N2O. The total pressure of the mixture is 192 kilopascals. What are the mole fractions of oxygen, nitrous oxide, and what are the partial pressures of each? So in this one, we've got pressure in kilopascals. Doesn't specify anything in particular for the pressure unit for part B. And since we're not using the ideal gas law, the units for Dalton's law of partial pressure aren't important as long as they're the same. So we can just keep this one in kilopascals if we wanted to. So for the mole fraction, that'll be relatively simple. We can just add up the total moles. So what we'll get there is 11.23, or 24 rather, 11.24 moles total. So for XO2, we would just do 2.83 divided by 11.24. And note with the mole fraction, there's no unit on there. I didn't put in moles for 2.83 or 11.24, but because they're both going to be moles, they're just going to cancel out. So the mole fraction is just the decimal value. And also note, it's always got to be between 0 and 1. If it was less than 0, that means we would have negative moles, which we can't have. And if it was greater than 1, that means we'd have more moles of that substance than we have moles total, which is just impossible. So for this one, we'll have 0.1 or 0.252, which means for the nitrous oxide, we could go through and plug it in. We could do 8.41 divided by 11.224, or what we could do is 0.25 and just, or 0.252 and subtract that from 1. So you think about it, it's a mixture of only these two components. So they've got to add up to the total sum. So if the mole fraction of oxygen is 0.252, that means the mole fraction of nitrous oxide must be 0.746. You could still use the mole fraction equation. So if you did 8.41 divided by 11.24, you get the same value there. Maybe rounded by like 0.001 different, just based on how the rounding goes sometimes, but should be the same. Oops. Or 4.6, and it should be 4.8. That would be missing 0.002 then. But yeah, if you did 8.41 divided by 11.24, you should still get the same value. So that gives us the answer for A. That gives us the partial, the mole fractions. So now if we want to get the partial pressure of each of these, all we need to do is then multiply them by the overall pressure. So not 292, but that'll be 192 kilopascals, or the same thing here. So when we think about it, since nitrous oxide is a much larger component in terms of moles, it's going to be a much larger component in terms of the pressure. It's going to be about 3/4 of the pressure. So 192 times 0.252, 48.4 kilopascals for the oxygen. And again, we could just subtract that number from 192, or we can just do the same multiplication, like 143.6 kilopascals. So either way, we'll get to the same. And then hopefully that's the same thing that the oh, this should be 144 since we only have 3 sigmas. All right, so we'll wrap it up there for this video.